So in the previous lesson, I showed you guys how to compare changes in concentration with the change of rate that corresponds with it in order to determine the order for each reactant in a reaction. All right. Now there's one other way to determine the order for each reactant, and that's by looking at a graphical analysis of each of the reactants. So I'm going to show you for zero order, first order, second order, how to look at the graphs and which graphs you should be looking at to determine what order you have. And then I'm also going to show you a couple of equations that you can work with in order to solve for some unknowns. So the first one, if you have a zero order reaction, remember the definition of a zero order reaction is that any change in concentration will not affect the rate. And so the way that we represent that graphically is if you plot the concentration of your reactant versus time, if reactant A is zero order, you would get a negative linear slope using your varying concentrations. All right? If this weren't zero order, then that line you would get by plotting the different concentrations would not be linear. It would be a curve. All right? Okay? We very rarely use zero order, but if you ever do see that the graph of concentration versus time is linear, then you know that your reaction is zero order. Let's look at first order reactions. So for a first order reaction, if you plot the natural log of the concentration of the reactant versus time, you will get a negative linear slope. You'll get a line that has a negative slope. All right. So that's specifically taking every single concentration, taking the natural log of it, and then graphing it versus time. All right. So let's actually look at what this linear equation would look like. So here I give you ln of AT equals negative KT plus ln of A naught. So let's make sure we understand what each of these variables is. All right, so the concentration at the start of the reaction, right when you begin, that's represented by A naught. That is your initial concentration. The naught, that zero, tells you that 0 seconds or 0 minutes, 0 time has passed. And the concentration after a specific amount of time has passed, we represent with AT. All right, so your other two unknowns, so you have natural log of AT, we know that that's your concentration after a given amount of time. Your K, remember, is your rate constant. T stands for your time, and A naught, remember, is your initial concentration. Well, if you notice, this is an equation, this is a linear equation, so that tells me that ln of AT would be my Y, my negative KT would be my MX, and A naught, natural log of A naught, is going to be my y-intercept. So why do we care about that? Why am I showing you y equals mx plus b? This is an algebra. Well, the reason why that's important is that your negative k is actually going to be your slope since t is your x. It's your x variable. Okay, so if you're given this graph and asked, hey, what is your k value? All you need to do is take the negative of your slope, and that will be your rate constant. All right? A couple of quick other things that I need to talk about before we actually work on a practice problem. Half-life. Okay, so just a quick definition. The half-life is the time required for the concentration of a substance to decrease by half. So let's see what that looks like. So let's say I start off with 100%. After one half-life, remember it's the time required for the concentration to decrease by half. So after one half-life, I have 50% of my original substance. After 2 half-lives, I have 25% of my original substance. After 3 half-lives, I have 12.5, and after 4, I have 6.25, and that would continue on and on and on and on. Keep in mind, this is never going to hit 0. It's just going to get smaller and smaller and smaller and smaller. So why do we care about that? Well, one key characteristic of a first-order reaction is the fact that its half-life is independent of the initial concentration, meaning as the concentration decreases for second order or third order reactions, your half-life is going to change based on how much you start with. For a first order reaction, regardless of where you are in the reaction, the half-life is going to stay the same. Okay, why do we really care? Well, here's why we care. If you were given a graph of concentration of your reactant, let's say X, for example, versus time, right? Remember, for zero order, it's linear. For first order and second order, it's not. It's going to look like a curve. Well, how the heck can I determine that this is going to be a first order reaction? Well, I could take the natural log of each of these concentrations and then plot it, or I could do something much easier. I can notice at time equals 0 hours, my initial concentration is 0.2. Then after 1 hour, it has halved to 0.10. Then after another hour, it's halved again to 0.05. Then after another hour, it's halved again to about 0.025. So what that tells me is that regardless of where I am in the reaction, my half-life will always be 1 hour. So that tells me that the order is first order. So if you're ever given a graph that looks like this and asked what's the order, check to see if your half-life remains the same. So here it stays 1 hour regardless of where you are in the reaction. Why is this valuable? Well, since your half-life remains constant, then I can actually create an equation in order to compare my half-life and my rate constant. And this is the equation. So your half-life equals 0.693 divided by your K. So you can use this equation really nice and easily to either determine your half-life given your K or to determine your K given your half-life. All right, so let's actually look at an example problem in which we use the equation that we just looked at, the ln of AT equals negative KT plus ln of A naught. All right, so it gives you this reaction and it tells me my rate constant is 0.410 minutes to the negative 1. And it tells me it's a first order reaction. So what that tells me is that I'm going to be using my ln equation. So for A, it says if you start out with 0.50 molar H2O2, what is the concentration after 10 minutes? All right, so I know I need to use this equation right here because I'm given my initial concentration and I'm given the amount of time and asked to find the concentration after that given amount of time. So that's why I know I need to use this equation. All right, so I'm solving for AT, so I'm going to leave that alone. I know my K is 0.410. I know my T, it's 10 minutes, and I know my A naught is 0.50. So I'm going to plug in all of those values right here. The only thing for this to be careful with, notice for my K, my units are minutes to the negative 1. Therefore, for my time, it can be in minutes since minutes to the negative 1 and minutes cancel each other out. If I gave you seconds, for example, or if your K were in seconds to the negative 1, you would have to convert one of them into the other unit. So just be careful with that. All right, so for here, I solve this. I'm going to just combine what's on my right-hand side together first. So negative 0.410 times 10 plus the natural log. It tends to be next to the regular log if you're having issues. So natural log of 0.50. And I get that the natural log of AT equals negative 4.79. Well, if you haven't done this in math yet, you might be saying, what the heck is natural log? Well, another way of saying natural log is simply log base E. Okay, and just from review from last year, remember to solve for that unknown, to solve for AT, you need to take E, raise it to the negative 4.79, and that will give you your AT value. And so your concentration is going to be 0.0083 molar. All right, let's look at the next problem. How many minutes does it take? All right, so 0.50 is my A naught. 0.10 is my AT. I know my K still, so now I'm just going to be solving for my T. So I'm going to plug in all of these values, and this one isn't too bad because I don't have to take the inverse of the natural log. I don't have to take E and raise it to a value. So you can solve this and you get 3.9 minutes, and that's your answer. Let's look at C. How many seconds does it take for half the sample to decompose? All right, you have two options here. First, you can simply plug in values to the ln formula, or you can recognize the fact that this is a half-life question and just plug it into the 0.693 divided by your K. I'm going to do both. So I'm going to start off with a natural log equation. It doesn't tell me how much I start with, right? But I know that half of it has decomposed. So I'm going to say that my initial concentration is 100, because why not? And my final concentration, my AT, is going to be 50. So I'm going to plug in all of these values. Okay? And when you solve this, you get 1.69 minutes. Now, notice it asks for seconds. So I need to convert this, multiply by 60 seconds, and you get 101 seconds. Okay? I'm going to also do this using the half-life formula. So I have my half-life equals 0.693 divided by K. Remember, your K is the 0.410, so I can simply plug that in, and I get that my half-life is 1.69 minutes, and I convert that to 101 seconds. So you can do it either way. Okay? D, how many seconds does it take for 15% of the original concentration to decompose? All right, I'm going to use this formula again. If I start off with 100 molar for my concentration, my A naught, what would my AT be? Well, if 15% has decomposed, what's left over? Well, 85%. So my AT is going to be 85. My ln of A naught is going to be 100. And then you just solve, and you get 0.396 minutes. Convert that to seconds, and you get 24 seconds. Okay, so a number of different ways to solve for your unknowns using this equation. Keep in mind that this equation can only be used if you have a first-order reaction. So what happens if I have a second-order reaction? If you have a second-order reaction, you are going to get a linear graph if you plot 1 over the concentration of A. All right, and notice that the slope here is going to be positive instead of negative. So if you get this graph, then you know that this is going to be a second-order reaction with respect to A. So this is my equation. Notice differences between this one and the one before. Instead of L natural log now, you have 1 over your concentration. And then also notice it's not negative KT since your slope is going to be positive. But again, you can do everything that we just did for the first order, solving for your unknowns, with this. And just like for your first order reaction, looking at this equation, 1 over AT would be your Y, your KT would be your MX, and your 1 over A naught would be your B. And so in this case, instead of your slope being negative K, your slope will simply be your K, your rate constant, if you have a second order reaction. So let's look at it. In this example, it tells me that I have a second order reaction and that the initial concentration is 0.95, so that is my A naught. My rate constant is 0.0045 molar to the negative 1 seconds to the negative 1. Keep in mind, I could give you your rate constant with those units and not tell you it's second order, because remember, it has to be second order if you have those units. So just to let you know, you might not be told it's second order just given the units, and then you could determine that it's second order just looking at the units. All right, it says, what will the concentration be after 3 minutes? So I'm given this. Notice my units are molar to the negative 1 seconds to the negative 1 for my rate constant. So I've got an issue. I'm given 3 minutes, while my units are molar to the negative 1 seconds to the negative 1. So I'm going to quickly convert the 3 minutes into seconds so that I can combine the K and the T. So I'm going to do 3 times 60, which is 180, and then I'm going to plug in all my values. So I'm solving for AT, right, because it asks what's the concentration. I know my K, 0.0045. I know my time, 180 seconds, plus 1 over my A naught. Okay, and so I'm going to get 1 over AT equals 1.8626, and now I need to solve for AT. So I'm going to cross multiply. I would get AT times 1.8626 equals 1. Divide both sides by 1.826, and you get your concentration, your AT, equals 0.54 molar. All right. For the next one, how long will it take for it to be reduced to 0.25? So again, I'm going to use the same equation, but now I'm going to plug in the 0.25 for my AT, and I'm solving for time now. Okay, so not bad, just simple algebra, and you get 650 seconds. All right, so I wanted to really quickly review with you because we now have 2 different sets of formulas. We've got your rate law, and then we've got these concentration versus time graphs. So if you're ever given concentration of AT, concentration of A naught, K, and time, you're given 3 of those 4, then you know that you're going to have to use this formula if it is a first order reaction, and this formula if it's a second order reaction. Okay. If you're given the rate though, and your rate constant and or AT, right? If you're asked to solve for rate or asked to solve for your concentration and you're given 2 of these 3 values, then you're going to be using your rate law. So if it's a first order reaction, you'd be using rate equals K times your reactant. If it's second order, it could be that reactant squared, or you could have 2 different reactants. All right. Now, what you'll be given on the AP, you'll be given this little piece of information out. 2 of these 3 look totally different from what we've been working with. Notice for the first one, it's ln of AT minus ln of A naught equals negative KT. Well, all they did was moved over the ln of A naught over to the left-hand side by subtracting it. Okay, so you can use either of these. Just make sure that since this is slightly different from what we just talked about, that doesn't mess you up. Same thing for the second order reaction. Notice they just scooted over the A naught to the other side by subtracting.